Hi everyone, and welcome to the Chaos Lab. Today, you're going to investigate the motion of a driven physical pendulum. And you'll see that when it's driven hard enough, it will exhibit chaotic motion. Pretty cool. Before you look at those videos, please make sure you read the handout thoroughly and make sure you can define the terms that I asked you to look up. I think those were chaos, phase plot, and fractal. All right? Now, before we start on the system that we're really interested in, I'd like to show you a different system that exhibits chaotic motion. This is a double pendulum, okay? And I have one right here. You'll notice how it works. There's a pendulum, okay, that's attached to a pivot by a frictionless bearing, and a second pendulum hanging by the end, attached by another low friction pivot, okay? How does this behave? Well, if the pendulum exhibits small amplitude motion, everything is simple and predictable. There we go. So here's a double pendulum in low amplitude motion. It looks a lot like a regular pendulum. There is a difference because there's a second pendulum here, so a second degree of freedom. There are actually two coupled modes for this system. There's the symmetric mode that we just looked at, where both parts move together. And then, of course, there's an asymmetric mode where they move in opposition. There it is, okay? Now, what's interesting is the behavior of this system when the amplitude is not small, but large. What's going on when it's large? Well, when the amplitude is large, there are two interesting things. First of all, of course, it's a double pendulum. But the second thing is that when the amplitudes are large, the restoring force on either pendulum becomes a nonlinear function of the angular displacement, okay? Because the torque goes like sine theta, not theta. Well, here, let's start out the motion and see what it looks like. Okay, you ready? Pretty wild. Here, I'm going to step to the side and let's watch this for a few minutes. Something that immediately jumps out at one is that the motion now is kind of unpredictable. At least when it was in chaotic motion, the motion was unpredictable. It would be very hard, maybe impossible, to predict the position of the two pendula at a point 10 seconds into the future. Here, let's start it again. Even though the system itself is relatively simple. The system itself can be described with a Lagrangian that you can easily write down. And you can use that Lagrangian to find the equations of motion, and then you can numerically integrate it to simulate the behavior of the system. But what you find is that the position and velocity of the pendulum at any point in time depends with unreasonable sensitivity on the starting conditions, so that a negligible change in the starting conditions completely changes the output at some function at some later time. In fact, it's so sensitive that people would say that perhaps the motion of an electron on Jupiter would have enough influence on this pendulum to change the outcome, maybe 10 or 20 seconds into the future when it's behaving chaotically. Finally, you can see that as energy leaks out of the system, it returns to regular motion. All right, well, that's a really stunning example, but we're going to actually look at a system that's even simpler, a single physical pendulum, but driven rather than undriven as this one was. Okay, I'll see you in a moment.